Hey out there. Welcome back to another lesson in AP Calculus. We are in Unit 7. Unit 7 is all about the definite integral and the indefinite integral and the antiderivative. In this lesson, we'll be looking at the fundamental theorem of calculus. This is one of the most important discoveries in the history of mathematics, and I just can't overstate its importance in so many disciplines. The theorem, though, is typically broken into a couple of different parts, and how it's broken up can kind of depend on the textbook you're using. Okay, but the way it's usually done is that it's broken into a part one, and part one is proved. Then part one is used to prove part two. So that's the logical order. But in reality, the second part is much easier, in my opinion, to learn first. So we're actually going to learn what I'm calling the second part of the fundamental theorem of calculus, or part two. And then in the next unit, we'll come back and pick up part one and complete the fundamental theorem. But you'll hear people say the fundamental theorem of calculus, and they basically mean the whole thing, both parts. But so it could be either one. So let's start with what I'm calling the second part of the fundamental theorem of calculus, even though it's just your first part. The fundamental theorem of calculus says that for a continuous function f prime of x on the interval from a to b, that the integral from a to b of f prime of x dx is equal to f of b minus f of a. Now, what this is saying is that if we want to find the area, or the definite integral, which is actually a signed area, but let's look at one just above the x-axis. That if we want to find the area under this curve and between the curve and the x-axis from A to B of this curve, and I'll call it f prime so that f is the antiderivative. Sometimes you'll see it called just f, and then they'll use a capital F for the antiderivative. Then what we do is we find the integral, the indefinite integral of f prime, and then simply evaluate at these two places and subtract them, and that will give us the definite integral. It turns out this word continuous can actually be relaxed a little bit in certain cases. But it still has to follow some pretty important rules. So we'll just start with the word continuous, and we'll look at special cases as we get there. All right, let's evaluate the given definite integral using a geometric formula and the fundamental theorem of calculus. All right, so from an earlier lesson, we should know how to do this. So let's go ahead and sketch it. 2x plus 1 is a line going through 1 on the y-axis. When x equals 1, it would be 3. 2, 3, 4. When x is 4, it'll be 9. So something up here. So we have a line. That's not really very accurate now, is it? Well, because I went a little too high here on this one. Let's bring this down. I was up at 4. Let's make it down at, there we go. That's probably going to be a little bit better. Not perfect, but better. Okay. So what am I looking for here? Well, I'm looking for, since it's above the x-axis, it'll be this positive area here. And we could break this down into like a rectangle and triangle, but I'm just going to use my trapezoid formula. So the area of a trapezoid is 1/2 base 1, which is actually this thing going up and down, which is 9, and this is 3. So 9 plus 3, the average of those two lengths, times the height, which is 3. 1, 2, and 3. So, lost my brush. All right, so that's 1/2 of 12, which is 6 times 3, so 18. I think that's right. Yeah. So now the fundamental theorem of calculus says that the definite integral from a to b of f prime of x dx is equal to f of b minus f of a. And sometimes you'll see it written where this doesn't have a prime and this is a capital F and a capital F. But whatever it is, it's saying that if you want to find the definite integral of something, find its antiderivative and evaluate the antiderivative at this number and subtract them. And it's such a common technique. We have kind of a neat little notation. There's actually a couple different ways people notate it, but I'll show you how I do it. So first we're going to integrate. This becomes 2x squared over 2, which is x squared. Integral of 1 is x. And I'm not going to put a plus c for a reason I'll explain in a minute. And then I just use these brackets around. Then I put the 1 and the 4 right there. Some people just put one vertical line and put 1, 4. Some people with the vertical line in front. Some people with the back. I just put them on both sides. So I'm kind of notation happy there. So now I'm going to evaluate this at 4. So I just plug in the 4. And that would be 4 squared is 16 plus 4 is 20. Then I put minus and always put parentheses to make sure you get this right, because now I got to plug in the 1. 1 squared is 1 plus 1 is going to be a 2. So this will be a 20 minus 2, which is 18. So you can see that we got the same result. So the fundamental theorem seemed to work here. Keep in mind, though, we were only able to find this area because this was a geometric shape. More in common ways, we're not going to be able to get anything but an approximation with a geometric shape, and we'll need to use the fundamental theorem to get the exact area. So I mentioned that I didn't need a plus c. Well, let me talk about why I don't. Let's say that instead I had kept that c, x squared plus x plus c. Okay, well then what that means is when I plug in 4, I would get 16 plus 4 plus c minus, now I plug in the 1 squared plus 1 plus c. But what happens is this negative is, so it's going to become 16 plus 4 plus c, then minus 1 minus c. Those two c's will be the same. No matter what c is, those will be the same and they'll cancel out. So we don't need it. So when you definite integrate, do not put a plus c. It could only just confuse you. But don't forget it when you do need it. All right, let's take a look at the next problem. All right, let's evaluate this. It didn't ask for a sketch, but just so that we have one, this is a parabola opening upwards, the y-intercept at 3. And we're looking for the integral from 1 to 2, which is going to be this kind of shape here. It's got a curve to it, so without calculus, finding this exact area, not possible. So that's exciting. All right, let's do it. So this becomes x cubed over 3 plus 3x, which we'll evaluate from 1 to 2. I'll plug in the 2 first. I get 8. Always start with the top, then the bottom. 8 over 3 plus 3 times 2 is 6 minus 1 over 3 plus 3 times 1 is 3. 8 thirds minus 1 thirds is 7 thirds, and 6 minus 3 is 3. And I'll just go ahead and add this together. 9 plus 7 is, let's see here, that's going to be, if I multiply by 3 over 3, 16 over 3. Okay, and that's it. So about, 5 1/3 is the area there. All right, let's try the next one. Okay, to take this integral here, what I need to do is, since this is a monomial in the bottom, I need to divide this into each one of these. So the first thing I'll do is I'll rewrite this as x minus 4 over x to the 1/2 dx. And then I'll divide this x to 1/2 into each branch. So integral from 1 to 9 of x to the 1/2 minus 4x to the negative 1/2 dx. Now it's ready to integrate. Let me go over here so I have room to do some arithmetic later. Up the exponent by 1, multiply by the reciprocal. Okay, up the exponent by 1, multiply by the reciprocal. And I'll be evaluating that from 1 to 9. All right, so I plug in 9, the square root of 9, 9 to the 3/2. Let's take the square root first. The square root of 9 is 3. 3 cubed is 27, but divided by 3 is 9, times 2 is 18. All right, this is just an 8. The square root of 9 is 3, times 8 is 24. Minus 1 to any power is 1, so that's just 1 times 2/3, minus 1 times 8. Okay, so this becomes 8 minus 24 is a negative 6. And then I'll just distribute this negative. So I have 6 plus 8 minus 2/3, which is 2 minus 2/3. And you can actually just call that 1 1/3 if you want to use mixed fractions. Or you can say, well, that's 6 over 3. That's 4/3. All right, let's do another one. Oh, didn't give myself enough room here. I'll tell you what, I'll just get rid of this one at the top and copy it over. There we go. Feels kind of bad to get rid of math, but oh well. All right, well, the integral of secant squared. What has a derivative of secant squared? That's tangent. So this must be tangent of x, which we're evaluating from 0 to pi over 4. The tangent of pi over 4 is 1. The tangent of 0 is 0, so the answer is simply a 1. So yeah, that's the area under this curve from 0 to pi over 4. All right, practice 6.1. I want you to use two right triangles to estimate the value of the integral of this from -1 to 2. And then, excuse me, use the fundamental theorem of calculus to get the exact value. Let's see how good a guess you can have. Pause the video and give it a try. All right, let's see what you did. So first of all, from -1 to 2, I would break this down into a right triangle here. And that's got a height of 4 and a base of 1. And so 1/2 of 4 times 1 is 2. But we're going to make it negative because it's below the x-axis. And then from 0 to 2, I can do another right triangle, again with a negative area, this time being 1/2 4 times 2, which is 4. Again, we're going to make it negative. So we're thinking this is going to be somewhere around -6. I'm thinking it's going to be a pretty good estimate. I think this one overestimated, but I think this one probably underestimated a little bit. If I had to guess, I would say we're going to be a little over. But let's find out. So to integrate, it'd be x to the 4th over 4 minus 3x cubed over 3. So I'm just going to call that x cubed from -1 to 2. 2 to the 4th is 16. And 2 to the 3rd is 8. Minus, plugging in a -1 to the 4th becomes a +1/4. And then -1 cubed is a -1, and minus a -1 is a +1. So then this becomes 16/4 minus 1/4 is 15/4. Minus 8 minus 1 makes a -9. So 15/4 minus 9 over 1 is equal to 15/4 minus 36/4, which is, well, let's see here. That's a negative 21, I think. Yeah, negative 21 over 4. Let me just, for some reason that's bothering me. I'm not. Yeah, 21. I had trouble seeing it. I had to rewrite it. So yeah, it's a little bit less than 6. A little bit more than -6. So I can't remember what I said. I think I thought it was going to be the other way. So I guess my eyes were wrong. But that's what it is. -21 over 4 is our area. Okay, what I'd like you to do now is go ahead and try these two practice problems, and then we'll go over it. All right, let's see how you did. This, you should have integrated this as the natural log of the absolute value of x. Now this 2, what are we going to do with that? Well, you could put it right here. You could also bring it out in front of the entire thing. So it's up to you. You want to play with the 2 or just wait till the end? Because we know we can pull constants out of both indefinite and definite integrals. So now the natural log of e is just 1. And the natural log of 1 is 0. So I just leave that 2 to the end, and 1 minus 0 is 1, times 2 is 2. So interestingly enough, that's the area there, just 2. All right, this one here, we're told to leave our answer in terms of e. Okay, let's integrate. The integral of 3e to the x is 3e to the x, which we will integrate from 0 to 2. Now, I plug in my 2. I get 3e squared minus 3e to the 0. Now 3e squared I can't do anything with. E to 0 is just a 1. So it's 3 e squared minus 3, or possibly you would see it written as 3 times e squared minus 1. All right, and on the next one here, we have a couple different areas here. Looks like they're going to counteract each other. What do you think that's going to become, positive or negative? Well, looks like there's more area up here than there is down here, so that'll be interesting to find out. Let's integrate. This becomes negative x cubed over 3. And that becomes a minus 4x squared over 2. So I'll just say minus 2x squared. And we're going to do that from negative 2 to 1. So plugging in the 1 gives me negative 1 over 3 minus 2. Minus, now I'll plug in the negative 2. I get negative 2 cubed is negative 8, but times the negative makes it a positive 8 thirds. Then minus, negative 2 squared is 4. So 4 times 2 is just 8. So let's see here. Negative 1/3 minus 2. I just like to go ahead and actually distribute that when there's a fraction and a whole number. So 8 and 2 will make 6. Negative 1/3, negative 8/3, and negative 9/3. Oh, how convenient. So that's a negative 3 plus 6 is 3. So that's our area of 3. Okay. So on 6.3, we're going to use a definite integral and then use a geometric formula to evaluate it. So we'll be using geometric formulas and the fundamental theorem of calculus. Okay, when we plug in 0, we get 0 minus 1, which is negative 1, but the absolute value of that is 1. If I plug in a half times 2 is 1, minus 1 is 0. So that's going to be that pivotal point where it switches direction. So I'll call that a half, and then we'll call this 1, and then 2, and then 3. 3 times 2 is 6, minus 1 is 5. So 1, 2, 3, 4, 5. So it's going to look something like this. And the area we're looking for is going to be all of a positive area because it's all above the x-axis, right? And we'll just use two different triangles. So this is 1/2 times 1 times 1/2, which is 1/4. And this is, let's see here, 1, 2 and a half. So we'll say 2.5 for the base, which would be 5/2, and then the height is, this one here is 5. So then that's going to become 25 over 4 plus 1 over 4, which is 26 over 4, or 13 over 2. Now, in order to evaluate this definite integral, we have to split this up into two different integrals. We know that this is equal to negative 2x minus 1 when 2x minus 1 is negative, which is when it's less than a half. So we're going to do from 0 to a half, we'll be using that. Then we'll go from 1/2 to 3 using positive 2x minus 1 dx. All right, so this will just be negative of that integral. So I'll go ahead and pull it out, and we'll up the exponent by 1. We get x squared over 2 times 2 is x squared minus x. And we'll integrate from 0 to 1/2. Plus, over here, we'll get x squared over 2 times 2 is just x squared, and then minus x, which we'll be doing from 1/2 to 3. All right, so this ends up being 1/4 minus 1/2 minus, that's just 0. Plus, this is 3 squared is 9 minus 3 minus 1/2 squared is 1/4, and then minus another 1/2. And I'm just going to kind of distribute all my negatives first and then see what I can combine. 6, and then minus 1/4, and then plus 1/2 again. So this becomes negative 1/4, negative 1/4, becomes negative 1/2, but then plus 1/2, which would be, ooh, no, what did they do wrong? Let me fix that real quick. Okay, well, it took me a second, but there's something wrong there. I was just doing bad addition. Negative fourth and negative a fourth is negative a half. I was forgetting that there's two of these halves here. Plus a half, plus 6, plus a half. All right, that looks better. So those go away, and then 6 plus a half is 6.5 or 6.5 or 13 over 2. So you can see they are the same. All right, well, hopefully I don't misadd anymore. Let's try the next one. Sketch the problem. Okay, so this is a quadratic inside the absolute value. The zeros of this quadratic would be at negative 2 and positive 2. And so what happens is instead of going underneath the x-axis, it's just going to be reflected upwards to 4 right there. And from negative 1 to 4 is going to give us an area of something like that. I'm not going to try and use a geometric formula because I don't have one. So I just need to use my Fundamental Theorem of Calculus. Okay, so we'll break this up and we'll make it from, this looks like negative 1 to 2 is when we need to use the negative. And I'll go ahead and pull out the negative. X squared minus 4 dx. Plus the integral from 2 to 3 will just be the regular x squared minus 4. All right, so now when we integrate, we get negative, and I'm going to use a square bracket so I can keep track of that. X cubed over 3 minus 4x evaluated from negative 1 to 2 plus the integral of, will be here, x cubed over 3 minus 4x from 2 to 3. All right, so this is 8 over 3 minus 8, and then minus, I got to plug in the negative 1, we get negative 1 over 3 plus 4. And then we have plus, and this one over here is going to be 8 over 3 minus 12. And then minus, not 8 over 3, that's 27 over 3. 27, 3 cubed is 27 minus 12, and then this is 8 over 3 minus 8 again. And would you believe it? That number is 11 thirds. But I went in and just did the math and then unpaused the video so you could didn't have to watch me do all that calculations. So you can simplify that yourself, and you should to double check. But 11 1/3 should be the answer that you get. All right, let's look at the next one. The sketch to describe the area R. Then write a definite integral expression for the area. Finally, evaluate the integral. Pause the video and give it a try. Okay, let's see how you did. So the region R is bounded by the graph of y is equal to 2x squared minus 3x plus 2, the x-axis, and the vertical lines x equals 0 and x equals 2. So we're looking from here at 0 and here at 2. Now, if you plug in a 0 to this equation, you will get 2. I wanted to switch colors here. Oh, I'm in the wrong. There we go. Make that one something else. Make this one black. There we go. So 1, 2. Now if I plug in 2, I'd get 4 times 2 is 8. Minus 6 is 2. Plus 2 is 4. So we have a curve like this. It is a quadratic equation, so it's going to be curved like that. And the area that we're interested in is this area here. And so to find that, we can use the integral. And since it's above the x-axis, the integral will give us the proper area. If it was below the x-axis and we actually wanted the area, we would just take the absolute value of it. So we'll do an integral from 0 to 2 of 2x squared minus 3x plus 2 dx. When we integrate, we get 2x cubed over 3 minus 3x squared over 2 plus 2x from 0 to 2. Now plugging in 0 to this is just going to be 0, so really we just got to do the 2. 2 cubed is 8 times 2 is 16, so that's a 16 over 3. 2 squared is 4 times 3 is 12 over 2 is 6, and then we have plus 4. So we have 16 thirds minus 6 plus 4. I'll just make them all over 3's. And that's going to give us 10 thirds. All right, let's take a look at our next one. Oh, I think that's it for this lesson, actually. In the next lesson, we'll be looking at more stuff to do with definite integrals and adding to our integration techniques.